All right, so before we've been talking about where the middle of the distribution is, right? Because that's where most of your data values lie. The next thing we're going to talk about is kind of how wide the distribution is. And so how do our data values go out away from that middle? So one way we can measure how wide a distribution is by calculating the range of the data. So range is literally the difference between the biggest and the smallest data values. So it's literally going to tell you how far you're going to travel if you start at the beginning of your data set and go to the end of the data set. So think of it just like if someone told you the range of a vehicle based on the size of the fuel tank and the MPG, right? It's the same idea here. So the range is telling you how wide that distribution is. So since we're doing a difference, we have to have quantitative data. And pretty much everything in this section, you've got to have quantitative data. But range is literally just maximum minus minimum. So biggest minus smallest. That's all it is for range. So let's say, for example, and I'm going to keep coming back to this data set today. So here I've got a corporation who hired 10 graduates. So we want to find the starting salaries for each graduate. And so we have that information, and we want to find what the range of those starting salaries are. So how do we find the range? We just look for the biggest and the smallest data value. So what is our biggest data value here? 47, right? And what's our smallest data value? 37. So our range is literally just going to be the 47 minus the 37, or 10. That's how you find range. All right, so range is the nice, easy way. But the problem with range is it doesn't really tell you so it tells you how wide that distribution is, right? It tells you where it starts and stops. But it's not really telling you how that data is going out away from that middle, right? So we need some more information. So most of the time, we're going to calculate standard deviation. So here I'm looking at standard deviation for a population, which means, is this a what? Parameter or a statistic? It's a parameter, right? What told you it was a parameter other than me saying its population? Greek letters, right? So notice here I've got the Greek letter sigma and sigma squared for variance. Variance is really just kind of a stepping stone to getting to population, to standard deviation. So for us, usually we're just going to calculate variance as a part of the process. So for a population, we're going to use sigma squared for the variance and just sigma for standard deviation. So in this case, lowercase sigmas. So to get to standard deviation, all you ever do once you have variance is take the square root of it, and that is your standard deviation. So the hard part is really getting to variance. And I will tell you, this formula looks worse than it actually is. The formula looks scary if you look at that formula, but it's really not as bad as it seems. So what are we doing in this formula? So basically we're saying, okay, I want the sum of the data value minus the mean squared. Or in other words, the sum of the deviations squared. So this data value minus mean we call the deviation. And we're going to square those and then add them up. So that's going to give us what we call the sum of squares. So your numerator for the variance formula is always the sum of squares. That's important because variance is really just sum of squares divided by n for our population. So if you just remember that variance is really just the sum of squares divided by n, that's going to help you out. That's half the battle. So that's where the variance comes into play. To get to standard deviation, every time we do standard deviation in this class, standard deviation is nothing more than the square root of variance. That's all it is. So it's one more extra step. Standard deviation is the square root of variance. All right, so I give you a step-by-step in the PowerPoint of how to find standard deviation, but I'm going to walk you through that process. So here is that same data set, and we're going to pretend for now that this is a population. So this is every single employee who was hired by this company. We're going to pretend that's true. And we want to find the standard deviation of these starting salaries. So to do this, I will always give you a table laid out just like this. So I'm going to give you a layout for this. And it's going to help a lot, I think, especially if you're a visual person. Basically, what this table is doing is it's walking you through the process of getting that sum of squares. So it's going to kind of take you step by step through it. So to start out, the first column, we're just filling in our x's. And remember, the x's are just your data values, right? So the x's are your data values. So that's all that goes in the first column, or just list out your data values. So in this case, that's 41, 38, 39, 45, 47, 41, 44, 41, 37, and 42. So step one, just list out your data values. And then what does this mean? The sum of the data values, right? In other words, add up the column. Why do you think we're doing that? Why are we adding them all up? Because we want the average, right? We want that mean for our next column. So to get mean, remember, it's just literally the sum of all the data values divided by however many you have, right? So we add up all these numbers. So 41 plus 38 plus 39, so on, all the way down. And what do you get? 415. So then now calculate your mean. So our mu in this case is literally your sum of x. So it's literally this number down here, 415, divided by however many you have, in this case 10. So our mu is 41.5. All right, so step one, list out your data values, calculate the mean. From there, the second column, you're building those deviations. So you're finding out, this is, so we call this the deviation, but really all it is the distance between every single data value and the mean. So how far is each of those individual data values away from the mean? So it's literally just subtracting. So 41 minus 41.5 to get negative 0.5. 38 minus 41.5 to get negative 3.5. 39 minus 41.5 to get negative 2.5. And you're going to do that all the way down the column. So 3.5, 5.5, negative 0.5, 2.5, negative 0.5, negative 4.5, and 0.5. So here's a good place you can check yourself, kind of. So add up all of these deviations. Get 0. I think that's a fluke. So what do you think it means when you get a 0 for this sum of your deviations? So first off, that's why we're going to square it, right? Because this isn't really helping us in terms of figuring out how far away the data values are, right? So that's why we square it, is because when we add up the sum of the deviations themselves, we get 0 most of the time. But what do you think that 0 is telling us? So think about what those deviations are, right? So what are these deviations? So it's not quite how many numbers we have below the mean and above the mean. It's really saying your data is kind of spread out evenly on both sides of the mean. So in other words, it's one way you can kind of get an idea that your data might be symmetric. So if we were to add all these up and we got a negative number, then that would mean more of your data is below the mean than above the mean, right? Or if you got a positive number, more of your data is above the mean than below the mean in terms of distance. So if you're getting 0, that's usually, and I'll tell you, for the ones we're going to do in this class, it's going to be 0 or very close to 0. But it's usually a good indication that your data is more than likely possibly symmetric. At the very least, you have an equal amount of distance between all your data points on the left-hand side and the right-hand side. All right. But for us, just know that this will normally be close to 0. For us, anyways. In the real world, not as much, but usually for us, it's going to be, because we're usually going to be looking at symmetric data. All right, so from there, this next column is literally the deviation squared. So you're just taking your values from that second column and squaring them. So negative 0.5 squared, go ahead and plug that in your calculator and tell me. So who got 0.25? Who got negative 0.25? All right, which one do you think's right? Positive 0.25. So why? The parentheses, right? So remember what's happening whenever you plug that into your calculator. Your calculator is going to follow order of operations. So if you were to put this in your calculator, negative 0.5 squared, like that, your calculator is following order of operations. So it's going to do the squaring first, right? So it's going to square that 0.5, and then it's going to multiply by the negative 1. So that's going to give you negative 0.25. But what do we know? If you're multiplying a negative number times a negative number, it should be what? Should be positive no matter what. So every single number in this last column should be positive. And so that's why I would put the parentheses around that negative, right? Because now that's basically, if you put that in your calculator that way, so the difference of having those parentheses, now your calculator's saying, okay, you want me to multiply by that negative 1 first to give you the negative number, and then square that negative number. So that's the difference, is if your calculator sees this, what your calculator is really seeing is this. All right, so then on down, so negative 3.5 squared, what should that be? 12.25, again, should be positive, right? And so we keep on going down, so 6.25, 12.25, 30.25, 0.25, all the way down to the last one, which is 0.25. And what do you think we're going to do next? We're going to add them all up. So what do you get when you add all of those data value, those numbers in that third column up? 88.5, yeah. So guess what that 88.5 is? That is the sum of squares. So the sum of this last column on the table is your sum of squares. So remember, if we go back and look, right, variance is nothing more than the sum of squares divided by n, right, for population. So that means once you've done the table, you have done the hard part of the work. And it's really not hard, it's just tedious, right? So once you've done that table and added up that last column, you have your sum of squares. So then to get variance, it's literally the sum of squares divided by n for a population. So our variance is going to be the 88.5 divided by n. What was n here? N was 10. So 8.85 is our variance. And then to get standard deviation is always just square root of variance. So standard deviation here is the square root of 8.85, which is about 3. I rounded to 8.9 when I did it on my notes. So. Now, one thing I will say, though, during the intermediate calculations, I would not recommend rounding much. So, or if you are going to round, because sometimes it might just be ugly numbers, if you are going to round, usually the good rule of thumb is keep 2 more decimal places at least than you want in the final answer. So if I said round your final answer to 2 decimal places, for example, I would probably keep 4 or 5 decimal places throughout the table and throughout all the calculations. Just because the more you round earlier, the more your final answer will be off. So you'll end up with rounding errors. All right, so that's population. Now remember in the last section, what did I say about the difference between parameters and statistics? So when we were talking about means, we got lucky, right? The way you calculate the parameter mean for population and the statistic mean for a sample, right, were the exact same. That is not true with standard deviation. So you actually have, it's very, very, very important to identify whether you're looking at population data or sample data. Because you're actually going to have a different formula for sample standard deviation and variance. Now it's very similar, but there is a difference. So the only difference in the formula, other than calling the mean x bar instead of mu, the only difference is you're now dividing by n minus 1 instead of n. So that's the only difference in the formula. But variance is still the sum of squares divided by n minus 1. Standard deviation is still the square root of variance. So literally the only difference, we calculate sum of squares the exact same way we calculated it before. Literally the only difference is what we're dividing by. So if you have a sample, you're going to divide by n minus 1 instead of n to get that variance. I will give you the formulas for standard deviation or variance, one of the two, because if you've got one, you've got them both, right? For population and sample on the test. So I will give you the formulas for either variance or standard deviation, one of the two. I will give you those formulas on the test. Now, I'm not going to tell you it's sample or population. I'm just going to have it listed exactly how it looks here. So I might have S is equal to the square root of the sum of squares over n minus 1. So I'm going to have it labeled like that. I'm not going to, and then similarly, sigma is equal to the square root of the sum of the squares over n. So I'm not going to tell you it's sample standard deviation or population standard deviation or variance, whichever one I give you. But as long as you remember Greek letters indicate parameters, right, you should be okay on that. All right, but I will give you one of these two formulas, and the same thing for population. I'll give you one of the two formulas on the test. And I will give you the table layout for this on the test. All right. So you don't have to memorize this formula, and you don't have to memorize how to lay out the table and how to do it. You just have to know how to fill in the table and whether you're dividing by n or n minus 1. All right. And that's just a simple matter of remembering if you're looking at S for sample or sigma for population. So let's go back to this same data set again, but now let's pretend instead of this being the population, these are starting salaries from one of their branch offices, the Chicago branch. And then they have several other branches, but we want to use Chicago to kind of estimate the starting salaries for the larger population. So we want to find our sample standard deviation of these starting salaries. Now it's the same 10 starting salaries. So luckily for us, we've already done most of the hard work in this case. We've already found our sum of squares, because the sum of squares does not change whether you're talking about a population or a sample. So we can go back to what we did just a minute ago for our sum of squares. This stuff does not change if you're looking at the sample as a sample. So all of this stuff is still the exact same. So our sum of squares is still 88.5. So the difference is now, we want standard deviation and variance. So let's go through variance. It's still sum of squares divided by n minus 1. But our sum of squares is still 88.5. So the only difference is now instead of dividing by 10, we're now going to divide by 9. So our variance in this case ends up being 9.8. And then now if we calculate variance, so square root of 9.8, so what do you get for that? 3.1. So in this case, this would be $3.1 thousand. Or if we wrote it out, 3,100, like that. Right, so that would really be our standard deviation. All right, so why do we go through all this trouble of finding this standard deviation? Well, basically, what standard deviation is, it's literally a measure of the typical amount that an entry is going to deviate from the mean. So in other words, most of your data is going to be one standard deviation away from the mean. Most of your data lies in that gap, basically. So the more your entries spread out away from the mean, so basically the wider the distribution is, then the bigger your standard deviation is. So standard deviation tells us how wide that data goes out away from the mean. So if I look here, so all three of these data sets have a mean of 5. And my standard deviation is increasing as I go across. So standard deviation of 0 means my data is not spread out away from the mean, right? So all of my data is right here at 5. So I increased that standard deviation a little bit. So standard deviation is 1.2. So then what that really means is, okay, most of my data is going to be 1.2 units on either side away from that mean. So between 3.8 and 6.2. And so if we look, so it's 3.8 somewhere about here, right? 6.2 somewhere about here. Does that encompass most of our data? It does, right? And similarly now, so notice it's not telling us anything about the shape, right? Because we go from a uniform distribution to a symmetric distribution to another symmetric distribution, but not what we normally think of with symmetric distributions, right? So it's not telling us anything about the shape other than how wide it is. So now, mean still 5, standard deviation is 3. So most of our data is going to be between 2 and 8. And is most of our data between 2 and 8? Yeah, it is, right? So your standard deviation just tells you where most of how far out from the mean most of your data is.